Alright, good morning everybody. Today is Code Forces round 664. I'll be competing in Div 1, so it'll be rated for me. But also, since it's going to be rated, I'm going to be spending less time like commentating. I'm going to do most of my work on paper probably. And then we have company. And then after contest, I will talk about the solutions to the problems that I know how to solve. Probably won't be all of them, but we'll see. So good luck, have fun to everyone competing. There will be an algorithms thread coming out later this week, so watch out for that. Yeah, feel free to skip to the end of the video if you're interested in solutions. Might be less interesting than usual to watch me compete this time, but I also have the mechanical keyboard back, so that should be fun. Alright, ready, go. Come on, give me the problem. Let's see. We want to sort it, right? So sort at the beginning, like everything less. Then like however many big. Yeah, okay, that's fine. Sure. So this is a group of D+1. 8 plus 15 plus 10 plus 23. Good sample. Good sample. Alright, so what's the solution? Did they tell us? 15, 10, 23. Oh. You can remove the first however many. Yeah, the first d plus 1 if you want. Answer 56? It's not. What? Okay. Oh, minus 1. Man, really? Am I misunderstanding the problem or something? One, two, 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 4, 5, 5, 6, 7, 13, 16, 16, 16. So initially I have everything less than or equal to 16. Then I skipped 2 days, so I've got the 21 and the 17. 21 and the 20. So what does this change involve doing? So it's like small stuff, then 21, 2 skips, 20. 2 things that would be skips. I'm going to take this out. I need to put something else here. Follow it twice. Then put something here. What was the first test case? 5, 8, 10, 15, 23. So a bunch of small stuff. And 23. I'll skip 2. So I see how to do this. So, lesson of the day is like do it on paper first. Okay. Number of extra spaces would be, we've got size, mod, we have no extra spaces, then it stays muted +1, otherwise it stays muted. That's nice. Alright, whew. A little worried about that one, but that's fine. Walks on a graph. The microphone's really far away from me, sorry about that. Audio quality's probably been bad. You've got a directed graph on n vertices and m edges. The out degree of each vertex is at most k. How big is k? Only up to 10. So it's not a general graph, but it's some sort of graph. Each edge has an integer weight between 1 and m. No two edges have the same weight. He likes to walk on the graph with some specific rules, which are represented by a tuple. If he stands in a vertex u, that degree I, the next vertex will be the edge the CIth smallest weight. see. Interesting. For the same size, then you have to take like the corresponding edges. They have the same out degree. So what is it? It's 1 times 2 times 3 times 4 times 5 times 6, 7 times 8 times 9. So there are 9 factorial answers. We just need to be able to check them really fast. Somehow. So how do we do that then? No two edges have equal weight either. Jeez. So loud. Yeah, maybe I just consider this here. So we've got 1, 2, 1, 2, 4. For 1 of weight, 4 for 3, weight 5, 3, 1 of weight 6. Well, if each node has out degree 1, and every node has to get back to itself, then you have this cycle. You always have a single cycle. I see. Okay, got it. So now the question is, because it's a Cthulhu graph, so the question is how many ways are there to pick a cycle? Where every node with the same degree is the same outgoing edge by sorted value. Might not have anything that has degree 1, so that might not even be helpful. If any two edges hit the same node, that's a problem. What if no two edges hit the same node? Well, can any two edges hit the same node? Does that... If every node has out degree 1 and in degree 1, you still might have 2 cycles, but that's fine. That's what we want. Yeah, so every node has in degree 1. That's what we're looking for. So how many ways are there of doing that? So if we have some node, what's our time limit here? 1 second. It's got an in degree here and an in degree here. it'd be this times 10, so it'd be 10 factorial. I think that's fine, if I remember correctly. Yeah, that's fine. So the question is, like, if we have this edge, what other edges can we not have? Well, it's more if we have this position equals this, can we have equal other value? Okay, that's fine. This is working out to be quite a cool problem. So now we can check that fast. This is the array we need to build. How do we do that? So for each n times 100, yeah. What in edges does this have? Okay. Good. Know how to do it. How are the standings looking? Not the end of the world. We can probably do all right. It's interesting, my rating went up because more bad people who are better than me solved problem A. It's kind of funny. Usually over time your rating goes down. But like more bad people are entering the contest now, which makes it better for me actually. Or more good people are entering the contest doing poorly. So they're given, yeah, single test case. What do we want? Just an edge array? Wait, they're directed. Okay, good. So Boolean. Oh wait, if we have 100, then it's 100 squared. Well, it's at most each edge times 100, right? Yeah. Okay. So this is max out by max out. Can other position max out, max out. So now, we just do this. Okay, so now 4, 5 goes 0. Might have 0 in degree, right? Yeah, so if incoming at I equals 0, size equals 0, then sys out 0 and return. Max out plus 1, or I guess it'll just be off by 1 slightly. Okay. So, oh, this is also common size. J is less than 0. Alright, so for each edge that's coming into us, have at e dot from size minus 1 e dot position and from, or I guess we can just make the from size be 0 based. That should be fine. It's true. C is less than A. Okay. If have CD, then legal or I guess this should just be illegal then. Is equal to A dot length. Then the answer plus plus. Turn the rise 4 into place equals 0. 2 place is less than the position at 2 place plus plus. Int previous equals 0. Previous is less than position at plus. If illegal, if we have A at 2 place, then we have the previous position at A at whatever the previous value is. Continue. At this position at. Otherwise, a position at equals 10 place. All perms at A, position at S1. So if you're of size 0, you go to the first one. Okay. You also can't have something of size 3 use the second biggest one. So this is right. This is the same thing. From node 1, you can't have it forced. That's from node 1, yeah. Okay, what's the other thing? The smaller of some choice. Yeah, that's also right. That has in degree 2, that has in degree 2. This has in degree 1. This also has in degree 1, so this looks fine. Oh, we never call all perms. I'm an idiot. Is int array x size solution at 0. Six nodes. 1, 2. Let's call them 0 based. 3, 5. So that's 2 to 4. That's a 1. 1 to 4 is a 2. 5 to 2 is a 3. 0 to 3 is a 4. 1 to 5 is 5. 4 to 2 is 6. 3 to 0 is 7. Oh, I see. We need an integer to each thing. Maybe that's not a problem though. If I never have integrate 2. Oh. Yeah, I think that's it. So that's 2, 1. It's also 1. There's a non-zero chance I get it wrong, so it'd be nice to have the comments back later. I guess let's just look over the runtime real quick. This collections.sort might be slow. Maybe that's an issue. Yeah, so it's 100N plus 100M, I think. Low overhead. Alright, what do problems look like? Yeah, probably C is what to go after. What are the clarifications? For some distance, you can perform operations on both S and T. Well, let's read the problem. Maybe we also read D, but probably C is the thing to work on. He defines a BN string as a string S of characters B and N. Okay, sure. You can remove the character of S, or you can remove B and N or NB from S, or you can add B or N to the end of S, or you can add that string to the end of S. So you can remove a character, you can remove a pair, or you can add a character or add a pair. Note that A is a substring of B. Yeah, okay. You know what a substring is? He thinks that B and strings ST are similar, if and only if they're the same size. And there's a permutation such that for all I, so one's a permutation of the other? He also defines the distance between two to be the minimum number of operations it takes to make S similar to T. He gives you n non-empty Bn strings and asks you to find n non-empty Bn strings such that T, such that the maximum distance to string S is minimized. What? I don't understand what we're doing here. He gives you n non-empty strings. You have to find one string that's like closest to the farthest one of the ones you're looking for. So it seems like you binary search the distance and then it's like, can you do it? So, but like, what is the similar? Why do we care about what's similar? Oh, minimum number of operations it takes to make them similar. Wait, what? Why does anything other than the number of counts matter? Surely just the number of counts of each letter matter, right? Why? You can permute this string to make T. If you can permute some string to make some other string, all that matters is the number of, like, the frequency of each letter. Or am I crazy? Can the string we print be empty? I guess I'll ask that. Probably doesn't matter. Yeah, I don't know that it matters. Yeah, so it looks like clearly the only thing that matters is how many B's and how many N's. So you want to minimize the maximum distance. So you just have like a pair of numbers. You got like, we don't care about this anymore. You've got some pair of numbers, AP. Please read the statement and ask to find, oh, not empty. Got it, thank you. Doesn't say that in the output section though. And ask you to find the minimum. Oh, it's even bolded. Ah! I see. Okay. Sorry people. I apologize for my incompetence. You'll just have to live with it. If you want me doing your contest, sometimes you get stupid questions. Okay. Thank you for answering it, though. So you have a bunch of pairs. So you've got like AB. AB can hit A minus 1 B, or it can hit A plus 1 B, or A B minus 1, or A B plus 1, or it can hit A minus 1 B minus 1, or it can hit A plus 1 B plus 1. So if we plot this on a grid, if you have a given point AB, you can go up, down, left, right. Or you can go up and right and down and left. So now you want to see what is the farthest 2 points that you can reach. Interesting. Or like maybe if you pick some point, how good can that be? We have an additional constraint on input, which is all of the values are not very big. All of the values are in like this area here. I mean, it's even stronger than that, really. It's like if you've got a lot of values, they're small. They're all not very far apart. So if you have some point, there's like, here we've got something. We have another cost function in this quadrant, and another one for this quadrant, and one for this quadrant. So this is just the max of the differences. And this one is the sum of the differences. This is max again. This is sum. So what does it look like? Things that are length 0 are just that. Things that are length 1 are this. Length 2 would be this. Yeah, I see. Okay. I think I see. So we've got some shape that looks like that. Where this right here is D, this is D, this is D, this is also D. And then this is D. I think we can solve this. Yeah, I think we can solve it. It's gonna have lots of solves though. So rating wise, I don't know, maybe not a great contest for me, but that's fine. So we need to, if we binary search the answer, then we need to, like we have, for each point, it creates some constraint, so it creates like x is greater than or equal to some value, y is greater than or equal to some value, x is less than or equal to some value, y is less than or equal to some value, which is really just a bounding box. Make some bounding box. And it also makes two, yeah, so you've got a bounding box, you also have two lines. You just want to see, is there any point in both? Well, you want to know a couple things, really. You want to know, like, are the x's legal? Well, okay, what is this? This is, this and this. So this is x plus, or what is that? It's the value of x minus y. The x is legal, are the y's legal? And then once we have that, we have this box that we can be in. Well, and then also are the x minus y's legal? Even if they all are, I don't know, I'm concerned you might have illegal constraints on the other axis. How could you actually find a case where that happens, though? Oh, like this, that would be a case. So otherwise, we might as well just use the top. Yeah, use the top corner. So either that one or that one. Okay, I think I see. So this is either min x, min y. Oh wait, maybe that's an issue. This This is a rectangle, really. Yeah, okay, so it's going to be either this corner or it's going to be this line intersecting one of the lines. So min x, min y, or one of these. Okay. Yeah, I think I see it. Alright, so let's start at least. I don't think this is 12 long, so that should be fine. Seems longer than 12. Yeah, it's definitely longer than 12. Okay. So, now what? Yeah, okay. So now I'm go to the bathroom. Okay. In the min, x minus y, max, x minus y. Max x would be int 1e6 and y is 0. Max y equals int 1e6. Min x minus y is negative 1e6. Max x minus y is int 1e6. Okay, that's fine. For each point. Plus distance. Same thing with y's. Alright, and same thing with x plus y's. Minimum it can be minus the distance, yeah. Okay, now we have to actually find the answer. Well, Otherwise, we might have an answer. Let's do this. So now we've handled lots of these cases. What we have left is simply this point here, this point here, give this bounding box. That puts in the answer will be in here. We have a point here. Yeah, this is kind of tricky. Let's make a physical model. So we'll do, I guess we'll do inches, that should be fine. So it's pretty much to scale. So now we have this point here. the Minkowski sum. Is it? I guess it's probably helpful to have this here. Oh, we just want the intersection of a bunch of them. Alright, so we want... the top right corner always work? How much time do we have left? 20 minutes. This is the hard part, I guess. We also have to worry about 0, 0. this is legal, return vec max x max y. Okay. Otherwise, there's some other cases. Yeah, okay, otherwise it's one of these. Alright, so otherwise, oh wait, okay, otherwise intersect the maximum x with the min x plus y. So max x, min x plus y, x minus y. Or the min y minimum y or the max y, really, it's the max y with the maximum x minus y. This is the min x minus y. Yeah, okay, so this needs to be where you have two of these lines, either like that or it's like that. It's exactly. Yeah, okay. So this is max x min x minus y. So that means that y, x equals max x, x minus y equals this, so y equals, or y equals x minus min x minus y. Max x, well, okay, int x equals max x, y equals x minus min x minus y. Otherwise, forced y equals max y, and x minus y equals max x minus y. So now x equals max y plus y. Okay. I think that should be fine. Ah, these are backwards. Wait, are they backwards? Maybe they're not. Hold on. The minimum x, D is a big number. Minimum x is 0. Maximum x is this big number. Less than min x or bigger than min y. Y is less than min y. Y is greater than max y. X minus y is less than x minus y. There we go. But that shouldn't matter. Oh boy. Interesting. Okay, I'm gonna go to the bathroom again. Wait, what? Min x, max x, min y, min. Oh. Got it. So let's look at this. 21, 22, 23, 24, 25, 13, 14, 15. Or 20, 21 to 25. Oh, okay. Yeah, we can do this, I think. So if max, what is this? Okay. So this is the min x minus y. So if the min x minus the max y is greater than max x minus y, the max x minus the min y is less than the min x minus y, and also return null. Okay, let's run it on everything again just to make sure.
Problem CDAC on answer test 8 set.
Test 8? That's probably an issue. Why would that be? Wrong answer even, not TLE. X, Y, min X, max X, min Y, max Y, this. It's less than min X, greater than max X, Y is less than min Y, Y is max, X minus Y is less than min Y, X minus Y is greater than max. And these are false. If X is less than 0, or Y is less than 0, return false. If both 0, return false. Min X, max X, min Y, max Y, min thing, max thing. Oh. That should be fine. Man, why is this wrong? Still gonna be wrong for sure.
Problem, feedback, unanswered test 8 set.
Darn. Oh, and Monogon got the one I didn't read. Nice job. Why is this wrong though, man? That's very unfortunate. I've got no idea why I'm wrong. Huh. Well, nice job, Monogon, on earning red, maybe? No, not quite. He needs, what? 200? Plus 200? Yeah, not quite red. Still a good performance by him. Top 100 in Div 1, that's definitely good. William also did quite well. Good job to him. Yeah, I wonder what on earth I'm doing wrong here. Can I see the test case now? Now the contest is over? No. I don't know. It's a mystery. Well, let's see. So OBS is still good. I suppose, I don't know. I like the problems. I thought the problems were good. It's a well-written set. It was nice that they gave us samples. Without samples, it would have been a little bit rough, I think. Or with, like, bad samples, at least. So, yeah. I don't know. I like the contest. I'm really disappointed I didn't get C, though. Because pretty sure this is how you do it. Yeah, I don't know. Maybe, I guess maybe I could add a check to see if it's actually in the bounds that I want it to be. But, I'm not sure. Let's look at the Div 2 problems. There are 3 problems I haven't seen before. It looks like it's a pretty steep difficulty fall off to this one. Alright, well, we can look at them. You've got this many R balls, this many green, this many blue, this many white. Pick a green ball, red ball, and blue ball, and change their color to white. It's possible to arrange the balls into a palindrome after several of the described operations. That's actually a really cool problem. I like it. So you can make a palindrome if all of those numbers are even except 1. So you can only have one of these be odd. Really, it's just the total number of balls, the parity of the total number of balls that matter. Because if they're an odd number of balls, then your answer is going to be odd. If they're an even number of balls, the answer is going to be even. Or like they all have to be even. So you might as well just make all of these white, right? So you just take whatever the min of all of these is, you make that many of them white. Oh, it's possible that's not the case. Well, it's always either 0 or 1. So there's that. Yeah, so either you do it 0 times or 1 time. That's not a very clean way of solving it, though. maybe there's a better solution. I think 0 or 1 time is good enough. Like, there's no reason to do it twice because you just put the parity back to where it was originally. So yeah. Alright. So that's problem A. Well, actually, I'm not actually going over them yet. We'll talk about them in a bit. I'm just reading them now. Playing chess as in plays. As we know, no employee can beat the boss in the chess game, so he's never lost any round. From the cell XY, you can move your chess piece as a rook. Rolls does at each cell once. Can you find a solution? You start at a given space, find a solution basically. Yeah, so yeah. You can imagine you start in the bottom left corner and then it's easy. And then you unshuffle the 2 rows. Alright, cool. So I understand how to do that. Let's talk about C now. You've got bit operations. He wants to play a game with you. You have 2 sequences of integers, this and this. For each I, you have to choose some j. Let ci be this first a, and some other b. Find the minimum possible c. Wait, what? Oh, find the minimum possible value of c1 or c1 and c2. Got it. So, yeah. So basically, you've got some array, or you have 2 arrays. You have to take each element in this first array and AND it with something in the second array. Then after you do that, you want to minimize the OR of all the things that are left. Oh, everything's so small too? So you can just brute force the answer even? Yeah, if you know what the answer is, then you just see for each thing in A, is there anything I can OR it with that would be a submask of what my answer is? Alright, cool. So let's go over the solutions then. So I can do solutions to, well, let me, okay. So I'll do solutions to all of the div2 problems. I guess that's it, right? So I can do solutions to div2 A, B, and C. D and E I solved in contest. In F, I'm pretty sure I know how to solve. Yeah, and that's it. All right. So let's talk about them. For problem A, I might be looking at this wrong. Wait, when is the answer no? Yeah, the answer is only no if you have 2 things of one parity, 2 things of another parity. Or I guess in this case, or you can't do the operation at all. Yeah, okay. So let's talk about the solutions. So for problem A, come on, give me a whiteboard. For problem A, you're given 4 numbers. So you've got like A, B, C, and D. On a given operation, if A, B, and C are all positive, then you can change this to A minus 1, B minus 1, C minus 1, and D plus 3. And you want to see, this is how many balls of each color you have. You want to see if you can form them, like make them into a palindrome. You rearrange them in some way after doing this. So what we can do is we can we can notice that you can make something into a palindrome if like there's only one way of doing it, basically, right? So you've got the thing in the beginning and the end have to match, and then the things before that have to match. And if you have an even number of things, every pair has to match up perfectly. But if you have an odd number of things, you'll have one thing in the middle which doesn't need a match because it's its own match. So that's what you're trying to make. The constraint on A, B, C, and D here is you can only have at most one of them is odd. Or 0 can be odd as well. 0 are odd? Oh well. This isn't a grammar problem, it's a math problem. So yeah, so that's the constraint. The thing to notice is if you do 2 operations, that doesn't change the parity of anything, because this will subtract 2, this will subtract 2, this will subtract 2, this will add 6. So it's only helpful to either do 0 operations or to do 1 operation. Those are the 2 things you can do, and then you can just try both of them and see if after doing 0 operations, do you have 0 or 1 numbers of these that are odd? If you're allowed to do 1 operation and then you do that 1 operation, do you have 0 or 1 things that are odd? And if either of those work, then it's possible. Otherwise, doing the operation multiple times won't actually help you because the issue is in parity, not in the actual values. So changing them more than twice isn't really any different than changing them just twice. All right, very cool. Let's move on to Div 2 problem B. Yeah, so, okay, in this problem, you have a chessboard and a rook that starts at some position, and you need to find some way of visiting all of the squares. So let's simplify the problem for a moment. What if instead of starting in any position, we start in the bottom left? Well, if we do that, there's a pretty easy way of visiting all the squares. We can go through all of the squares like this, and then we can go over by 1. Then we can go through all of the squares like this. Or do we have to end up back at the same square? Visit every cell exactly once, even. Yeah, you don't have to return to the same one even. So you can just go like that, then you can go over 1, go like this, and now you can just make this path. And when I say go like this, you hit each of these positions once. So if you start in the bottom left, this is a very easy problem. You can just do this, it's very easy to code. The issue is, what if you start somewhere in the middle? Then it might get a bit more tricky. Well, what we can do is we can actually just swap the rows around and it won't matter. Because during each move, your rook either goes up, or it goes right, or left or down, but it only changes either its row or its column. So if we take 2 chessboard rows and we swap them, any move that you would make in the original board will correspond to the same move in this output board. So basically what we can do is we'll turn each one of the positions in the original board to some position in this swapped board, basically. Let me formally show how to do that. Or I guess more, not really formally, but just to give a better example. So let's say you want this to be your starting position. Then you can make this 0, 0. You can make this 1, 0. This 2, 0. Then this will be 3, 0. This will be 4, 0. We have company?
I guess think so.
So then it'd be like that. So this is kind of what your board looks like. And then you imagine that really your board is like this. But this part just kind of gets folded over down to here. And then you have this part over here, which gets folded over to here. This part here, to use a different color, gets folded over to this. You can just do this with modular arithmetic very easily. So now once you have this, you can just do your path on this board, and you just convert your output to what it would be in the original board. So that's the entire problem. That should make it pretty easy to code. I'm sure there are lots of other like construction ideas that you can use without doing this conversion. So maybe there's some other way of just like, maybe you can do everything here and then go to some other row, do everything here. On your last space, go to the next row, do everything here. And that probably works too. Yeah, okay. So basically another way of doing it, I guess, that I just figured out would be you could just repeatedly go right. And then here, instead of going right, you'd go to the last space, then you keep going right. And now you go up one. And if you're at the top, when you go up one, you really go to the bottom row. You just keep doing that till you visited all the spaces. That'd be another way of doing it. It's pretty much the same as what I described, except like maybe less convoluted. All right, problem C. I just remember the problem. So basically, you're given two arrays. Both are very small. They're only size 200. And then all of the numbers in the arrays are also small. They're only up to 2 to the 9th, so they only have 9 bits. Then on top of that, what you want to do is find the minimum possible value of the OR of all of your resulting numbers. The operation you're going to do to these numbers is you're going to take each element in the first array, the array A, you're going to pick some number in array B, and you're going to take the bitwise AND. So if you don't know about bitwise AND and bitwise OR, you should read up on them, because I'm not going to explain them here. But they're important things to know because they come up a lot in competitive programming. So here's the observation, right? For all of these numbers in this C array, any number we pick, all of its bits will be in the final answer. So if we don't want, for example, the 16-bit to be on, then we can't pick any C number that has that 16-bit on. We can only pick C numbers that are a subset of the bits that we want to have on. So what we can do is first we can brute force our answer. Now we know what the answer is going to be. When I say brute force, I mean we're going to say, imagine the answer is going to be 7. Now we check, can we make 7? So we'll just keep checking all of these numbers. Eventually we'll be able to make something that's less than or equal to 2 to the 10. Or I guess less than, strictly less than 2 to the 10. So we check all of the numbers from 0 up to 2 to the 10. We want to see, can we make each of these numbers? So now if we know the number we're trying to make, we have some number in A, maybe that number is this. And maybe our answer that we're brute forcing, so we've got this in a for loop, maybe our answer will be 1, 0, 0, 0. Now what we have to do is we have to take this number, and we've got this array B over here. We have to find something in B that we can AND this with in order to get some submask of this. So we can brute force all of these possible things. And the runtime here will be, let me just make sure the runtime's all right. Yeah, it'll be 200 squared times 2 to the 10. So how big is that? Let me just be sure this is going to run in time. 4 times 10 to the 7, so that should be fine. Should be 0.4 seconds. You've got full second. All the operations are super quick as well. So that's the idea. So we brute force what this answer is. After knowing what the answer is, then for each element in A, we make sure we can find some element in B to AND it with that will make it only be a subset of the bits that we are allowed to use. To do that, like to check if it's a subset, so let's say this is your A number. So you want to check if A number and your B number, these are just elements in your array, if this number is a subset of the answer. So if this number and the complement of the answer is equal to 0. So this complement means all of the bits that aren't in the answer. If this is possible, or if this is equal to 0, that means you're a subset of it, which means that this is an okay B choice for this A choice. Yeah, okay, that's the idea for that problem. Let's move on now. So these were the Div1 problems. I thought they were all very fun to solve, or at least the 3 ones that I did solve. The 3 ones that I think I've solved, the 2 of which I got AC on in contest. I don't know why I'm wrong for the hardest problem in Div 2 or problem C in Div 1. So for this problem D, div2D, div1E, here's the idea. So you have a bunch of numbers that you can pick. Let's do the first sample, because that's pretty good, I think. 5, 8, 10, 15, 23. So you can take these numbers, and then also we have like some m equals 11, and then some d equals 2. So what happens here is you can take these numbers, you can shuffle them in any order you want. After you do that, you want to make it so that the numbers that you actually get points for are as big as possible. When do you get points for something? You get points for everything, unless you pick something that's bigger than m. Let's say we picked the 15. Then the next d things we don't get points for. So if we pick this 15, then we wouldn't get points for the 23, or if there were something here, we wouldn't get points for that either. Okay, very good. So in this case, the best you can do is you can, like, one thing you could do that would be better than this order would you could do 5, 8, 10, and then the 23, and then you might not get the 15. So if you do this, then your final score will be these three things, plus you get the 23, you don't get the 15. You can actually do better though. And the way you can do that is you could do 15, then you could not get this 5 and the 8. Then you could get the 23, and you could also get the 10 before the 23. So then you could get the 10, and then you get the 23. So that would be your final order. So what we've done here is, like, basically we pushed the, so initially our first answer is we get everything under the value of m. So we get all of that stuff first. Then we get as many big things as we can while throwing away the big things we don't want. Once you've done that though, you can make some trade-offs, which are you can get some more big things and replace small things instead. So that's what we'll continue doing, and then we'll do that as long as it's beneficial for us to continue that pattern. All right, so what does that look like? So there are two things we can do. The first thing is, in this case, we're gonna get one of these big numbers, the numbers bigger than the cutoff, that we weren't able to get originally. This 15 comes after the 23, which means we can, like, we have this extra, like, here's like a spot that we're not using. We can move all of the big things over by 1. And if we do that, then we need to delete 2 small items in order to place this 15. So we'll want to delete the smallest of them, obviously. And we look at the sum of the first 2 small items and see, can we replace the 15 with those? If we do, is that beneficial? In this case it is, because 5 plus 8 is less than 15. So we subtract 5 and 8 from our previous answer and add 15. Now, there's another case instead, which might be a little bit different, and that is, imagine if we had something like this. So imagine we had 5, 8, 10. We initially wanted to have all of those. Then we have this 23. Maybe we have some 12s here. So we've got a 12, then we have another 12, and now we have a 15. Yeah. So if we do this, initially the points we get will be everything that's small. Then we'll get the 23, and then we'll want the 15. So we'll delete these 12s initially. So now what we're going to consider is, what if we put this 15 in the beginning? Then what would that do? Am I wrong on this? I might fail system tests. Give me a sec. This is a good case. Should have checked it. So you can put 15 in the beginning. Yeah, there's a very good chance I fail system tests. Why is my solution right? Darn, did I just fail? Yeah, I failed. It's unfortunate. Huh. Gotta be more careful. Well, my rating's going down. I might have just lost red. That's kind of fun. It's a little bit mean, isn't it? Is Ava getting hacks on A? Hacks on B even. Oh my goodness, this is a dangerous round. This is a dangerous round. Well, I really like to know whether this is right. Because if I got no problems this contest, I'd be very sad. Sorry, I know we're supposed to be doing the problem review at the moment. Yeah, okay, so... how do you actually do A then? Interesting. Yeah, so initially we would get these. If instead of this being a 12, let's say this were a 13. Now, in order to get this, or let's say 14, that way it would be beneficial. Alright, back to this solution. Here's where one way you have to be careful. Apparently there are other ways as well, though. We would want to replace the 14 with the 5 and the 8. But in this case, you can't actually do that. The reason is that if we get rid of the 14 and replaced it with the 5 and the 8, then we can't move this over 1, basically. We can't, because then we'll lose the 15 as well. So in addition to losing these two small things that would come after the 14 originally, we also would need some other small number to come after the 23. So we have to pay for the additional small number in this case, which makes it not worth it. Yeah. Okay. Well, then there's some other case that I'm not handling. Apparently. Past pretest, failed system test, though. Is it an easy thing I can read now? Did you see what it is? No. Okay. Alright, let's talk about this problem B. This guy walks on a graph. So you have some graph, and you have a bunch of edges, and you want to make it so that... Oh man, it's difficult to explain. Yeah, you want the out degree... Oh man. So you want the... You want to pick like some like set of numbers where like you... So you're gonna pick the maximum out degree. What is that called? They call that K. So you're gonna pick K numbers. The first number will always be 0, or I guess it'll always be 1. Then the next number will be 0 or 1. The next number will be it'll be 1 or 2. The next number will be 1, 2, or 3. The number after that will be 1, 2, 3, or 4, etc. And what this means is, if you have some number that has an out degree of 1, you take the first edge. If it has an out degree of 2, you take, like if this is a 2, that means you take the second edge. If it has an out degree, the second largest edge. If it has an out degree of 3, that means you take the third largest edge. If this is a 3, if it's a 2, you take the second largest edge. If it's a 1, you just take the first one. So that's the problem. Now, what you want to see is how many choices of this are there, so that in the end, every number or every node in the graph can take some path and get back to itself. That's the problem. Now, yeah, okay. So, how do you solve it? Well, if every number in the graph, like every node in the graph has an out degree of 1 after we've picked this permutation, we want to make it so that every node in the graph also has an in degree of at least 1. If some node has an in degree of 0, then you can leave that node, but you can't ever come back to it. Also, the total out degree of all nodes will be n, which means, like by the pigeonhole principle, we need the total in degree of all nodes to also be n. So you can't have any node that has an in degree of 2. And that's what we're going to try and enforce. It's also pretty clear that if we leave some node, we have to finish some cycle. And if that cycle ends at this node, we have a path back to our node. If it doesn't come back to this node, that means we have some node here that has an in degree of 2, which is what we were trying to avoid. So basically, the problem is like, can we do this thing? Can we assign these numbers? Can we pick this group here in such a way that no node has an in degree of 2? That's what we're trying to do. If we can do that, that's the answer. Or that's one answer. The other thing is we only have 9 factorial possible choices. So the biggest the answer can possibly be is 9 factorial. So we're going to brute force all of these possible choices, and we're just going to very quickly figure out for one of these, will it work? So now, in order to help us do this, we're going to keep some array, which is like, I called it illegal. So it's a 4-dimensional array. What it means is, if the number at position A, this is position A, if this number is B, that means, is it illegal for the number at position C to be equal to D? So if that is the case, that tells us, well, when we're at position A, if it's illegal for us to place a B, if at some previous position there was a D, that means we can't actually place this B. If we do that, then we can like see what our permutation is, and we can validate our permutation in 9 factorial times 9 time. So fast enough. This is like pretty much equal to 10 factorial, which is fast enough. Yeah, so how do we build this array in a fast amount of time? Well, the size of the array is going to be, this is about 10, this is 10, this is 10, and this is 10. So it's not that big of an array. And we can fill out the numbers in a smart way. For each node, if we've got some node here, we want to look at all of the edges that come into it. If you ever have two different edges that are in the same position from 2 nodes with the same degree, then you can't ever pick that number. Like these edges can't be picked, because if you pick one of them, you'll also pick the other one. So first we'll handle all of those cases. That's like I call it can't pick. So that means like if you have something of size A, you can't pick anything of size B. And yeah, that's the idea. So there are certain edges that you can't pick because you have 2 that both hit the same node. In addition to that, there are certain ones that are illegal. So namely, if we pick this edge here, then we can't pick this edge here as well. Like if we have this is size 5 maybe, this is size 3. If we pick the one of size 5, we can't pick the one of size 3. Yeah, okay, so there's that. Did we pass this problem? We don't know. Alright. So yeah, that's the idea behind problem B. I'll show my code, which might be wrong. Basically, for the recursive part, you just try all permutations. The things that are illegal, that also you might be able to pick, those are fine. Otherwise, you continue. And just like ignore it. Finally, if you're able to place all your positions, then you increment your answer. So that's the recursive part. If you're actually building these 2 arrays, that's also pretty easy to do. If you've seen two edges that have the same, they come from the same place and from the same position, then you can't pick that place in that position, because then you'll automatically have an n degree of 2. Otherwise, you can do this thing, which is basically you consider all possible types of edges. For each edge, you do an order 100 double for loop. So the total runtime here will be number of edges times 100, plus number of nodes times 100. And if you have any two pairs, you can't pick both of those pairs. So we just mark that as illegal. All right, that's problem B. For problem C, if I'm understanding it correctly, the idea is that you have, like, basically they give you the problem in terms of strings, but I don't think the strings are really relevant at all. Really, you just have like a bunch of points on a 2D plane, and you want to pick some other point where you want to minimize the distance to the farthest other node. Holy cow. Jeez, it's loud. Okay, you want to minimize the distance to the farthest other node, and you want to pick this point so that you do that, and you also have to print what your point is that you pick. Now, all of the other nodes are like randomly dispersed across the grid. They're also all positive, and they also have this additional constraint, which is kind of weird, that the sum of the x values plus the y values is minimized because of how these things are picked. But the movement is what's particularly interesting. In one time step, you can move in all of these directions. You can't move like this, and you also can't move like this. So the number of things that are a distance 1 away from you are all of the things that are in this shape here. Things that are distance 2 are like this. And that's the idea. So my solution was, this is like the current distance. This here is D. This is also D. And then this distance right here, if you go by like Manhattan distance, is D. So my solution was, I'm going to binary search whatever D is. And then after doing that, if you have a bunch of points, maybe we have points like this, then each one of them has some restriction of where we can actually, like where the center can be. So it's like, well, the center has to be somewhere in like this, it's got to be somewhere in this shape. So now we want to find the intersection of a bunch of these shapes. And to do that, what I do is I just like store the, like we have a bunch of these left bounds, a bunch of these right bounds, bottom bounds, top bounds, and then a bunch of these bounds that are kind of weird. So I just take the most constraining of all of those, and now I just check, so now like the top left, down, and right, those bounds will just form some rectangle. And now I have these two bounds that look like this maybe. There are two different cases. I say either this top right point is legal, in which case we'll take the top right point. Otherwise, we have something that might look like this. So now I either take this point here, I intersect these two lines, and I take that point here, or we have something that looks like this, in which case I take that point here. And that's some point that's good enough for everything, and then I can print that point. So that's my solution. It's wrong somehow. I don't know why. Might be an implementation detail, might be something else. Yeah. So it's pretty disappointing that I failed A. I'm not a fan of that. And I might be losing red because of it. Like, it's pretty likely, to be honest. So then that means the next contest will be a road back to red. That'll be fun. Yeah, hopefully we can earn it back. And it looks like it's quite likely Monogon actually did get red then, if he solved A correctly, and then he also got B and D. So we'll see. We'll see. It's an exciting scoreboard result, to be sure. That's all. Thanks for watching, and have a good day. Hopefully you didn't fail as many system tests as I did. Goodbye.